Okay, we have some nomenclature here to start with. So we learned how to name organometallic compounds. If you recall, the metal is the parent name or the base name. So here in the first one, it is lithium. And the organic portion coming off of that, it will be named as a substituent. And of course, your substituents go out in the front in alphabetical order. So here we have C6H5. That's a condensed formula for a phenyl group, if you recall, from last semester. So this is simply phenyl lithium. Our next one here, the metal is magnesium. That is our parent or our base name. Set my timer so I know when my battery goes dead and switch. Okay. The organic portions coming off is just named as substituents. So as a substituent, we have a 6-carbon ring there. That is a cyclohexane. But as a substituents end in YL, so that's cyclohexyl as a substituent. And then we have an ethyl on this side. They go out in front in alphabetical order. Cyclohexyl, ethyl, magnesium. Now, we also talked about that if we have anything other than a carbon coming off, we name that as an anion and named out as a separate word. So if we were to have something like this one. Here again, magnesium is the parent name or the base name. The organic portion is named as a substituent coming off the metal. That's as a ring itself, that's a cyclopentane ring, but as a substituents end in YL, so it's cyclopentyl, the YL. Goes in the front. But then we have the bromine. So anything other than a carbon, we name that as an anion as a separate word. So as an anion, a bromine is a bromide as an anion. We have fluoride, chloride, bromide, iodide as anions, those halogens. So that goes out as a separate word completely at the end, because it's going to be a separate word. So this is a bromide. Okay, so this one is cyclopentyl magnesium bromide. And there will be a space there. It's a separate word. Any questions on the nomenclature of the organometallics? So I wanted to throw that in there because I didn't have one on the old test, but we did cover that. Our next one here, we were looking at a mechanism question. So if we notice, first step of the mechanism, these organometallic compounds, whether it's organolithium or the Grignard, the magnesium, both of those we talked about are very, 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 very strong bases. Those are our strongest bases. So because we have a strong base, they can act as a nucleophile. We have been using them as nucleophiles, but because they are a strong base, and strong bases are very fast reactions, you need to first look and see, do I have any acidic hydrogens that might destroy my Grignard or organolithium? And we do have an acidic hydrogen. Alkynes, a terminal alkyne is acidic. That has a pKa of 25. So this carbon here does have a hydrogen off that has a pKa of 25. So that is acidic. Now, our methyl lithium is going to come and grab that acidic hydrogen. We'll leave the electrons there on the carbon. If you want to, so the CH3 group grabbed the hydrogen, you will have CH4 if you want to show that. You don't have to. That's just methane gas and it bubbles out and it's gone. So I have destroyed my original organolithium compound. But lithium will balance the charge out here. And so even though I destroyed my original organolithium, this particular one makes another one. So that will be the case if you're grabbing acidic hydrogen off of a carbon. It's not going to be the case if it's acidic hydrogen on an oxygen or something like that. You just completely destroy your organolithium, organomagnesium, either one, and they're gone. But this one, we make a new organolithium compound. So even though I destroyed this one, we've made a new one. So it's that one that's going to react here in our second step. Second set of reagents, I'm adding in this ketone. And it's this organolithium compound that's going to, we got partial positive charge on the carbonyl carbon, so it's this carbon that will attack the carbonyl carbon and kick the electrons up onto the oxygen. Now, anytime you kick electrons on the oxygen, just take a quick look, make certain they can't kick back in and reform the carbonyl if you have something you can kick off. And we don't. It's all carbon-carbon bond, so it's stuck here. Until the last step, we add in acid. Ammonium chloride is an acid. There's a full plus charge on that nitrogen, full negative charge on the chlorine if you want to show that. But it's the ammonium group that's the acid part. So this will pick up a proton off of the nitrogen. Then that nitrogen can become neutral, so that's why it's a good acid. And that gives us our alcohol as our product. So there's the product. But there's the full mechanism. All my curved arrows on how we get to that product. So I gave you the starting materials and the product. You just have to provide all these curved arrows and show how we get there. Questions? So I don't know what mechanism I'm going to ask on the exam, but I will more than likely put a mechanism question on there. You can pretty well expect that. So we have covered a few different mechanisms. So be prepared on those. Some I told you I wouldn't ask. Some I showed that I said I would not ask. So the ones I can think of there, I did show the mechanism on how we formed the organolithium and how we formed the Grignard reagent, and I said I would not ask those. So I will stick to my word. I will not have one of those mechanisms on the test. But I did go through them, but I won't ask those. But any of the others are fair game, or any combination thereof. Okay, our next one here, we are looking at UVB spectroscopy. And so we talked about that. We said that the more conjugation that you have, the longer will be the wavelength of light that it absorbs that. It will absorb that UV vis light at a longer wavelength, the more resonance that you have. If you look at these structures, the first structure there, look for the most conjugation that you have. You're looking at what is the maximum amount of conjugation that's within the molecule. So if you look at that one, the most double bonds that we have that are conjugated is 5. These here are all conjugated. They are adjacent to one another. So I've got 5 here. Over here we have 4 that are conjugated. These are conjugated. But we have sp3 carbons that's acting as roadblocks. So these are isolated from these. These act independent from these. So the most conjugation that we have is 5 double bonds in that structure. If you look at the next one, the most that we have that is conjugated in this one that I see is 6. All of these are conjugated. They are all adjacent to one another. I have 6 that are conjugated there. Up here we have 2 double bonds that are conjugated. But those 2 are isolated from these 6. There's sp3 carbons here that are acting as roadblocks that isolate those 2. So the most that I have that is conjugated is 6 in that one. In the next structure, the most that we have that is conjugated is 8. All 8 of those are conjugated. Now we do have one sp3 carbon here that's acting as a roadblock right there, but they are conjugated around this way. See, we're still conjugated across here. There's sp2 next to an sp2. That one's next to an sp2 and that one's sp2. So all of those were conjugated through here. We do have the one roadblock here, but we're going around that. Still conjugated around that. So I have 8 double bonds that are conjugated in this one. The last one, I'm not going to draw that one up. The most you have there is 3. If you look at that one, you got a lot of sp3 carbons in there in between. So all 4 of those, you got some phenyl rings there. You got 4 phenyl rings out there. Those 4 phenyl rings are all isolated from one another. So the most conjugation you have there in D is 3 double bonds. Each phenyl ring is conjugated, but they are isolated from the other phenyl rings. So the most you have in that one is 3. So the one that has the most conjugation was C here. It's got 8 double bonds that are conjugated. It will absorb light at the longest wavelength. Questions on that? Question 4, we're looking at some reagents. I've given you one of the starting materials, and I've given you the product, and I want you to tell me how we go from that starting material to that product. Let's look at the first one. Okay, let's see what we can come up with. Now, sometimes it might be difficult to see it going forward. Sometimes I think they're easier to go backwards. Go to the product and work your way backwards sometimes. Sometimes I might just work a little bit backwards and then kind of go forwards and see what we can do to get there. So I think this one is a little bit easier going to the product and going backwards, because when I look at that product, what I notice when I see that product, I see a 6-membered ring with a double bond. 6-membered ring, double bond, that's Grignard. Sorry, I said Grignard, didn't I? I meant Diels-Alder, sorry, I was still back on the other question. This Diels-Alder, when I see a 6-membered ring with a double bond, that's a Diels-Alder product. So I think this one is easier to go back there and try to do a retro Diels-Alder, and then we can see how we can take that to one of those materials. So like we talked about this morning, you find the 6-membered ring with the double bond, go to that double bond, highlight that, extend 1 carbon on each side, and then cleave it apart. So those 4 carbons you've just highlighted must be the diene. So make that a diene. And the other part will be the dienophile. So these 2 carbons I'll put in blue, that's going to be my dienophile. Got an alkene. These are both wedges, so they're both on the same side. They need to be both on the same side here. So adding those 2 compounds together will give that product. Now, how can I take this to one of those? Okay, I think you can quickly see which one we're trying to get to. It's this one has to go to this. So how do I get 2 double bonds on there? Well, we make double bonds, if you recall from last semester, we make double bonds using elimination reactions. E2 was the best. We can do E1, but we like the E2 reaction, some type of E2 reaction. So if you were to do some type of E2, this had to be some dihalide to get 2 double bonds. You had to have a dihalide with some strong base, and that would do 2 E2 eliminations. So you might can see what would happen here. If I take this and say add bromine, that will give me my 2 halogens that I need, because I need 2 halogens to be able to do a double E2. So bromine will add across the double bond. You get a dihalide. And then if I take that and react with 2 equivalents of a strong base, then my strong base is going to pull off beta hydrogen. Alpha is where the halide is, so let's just take a look. Here's an alpha position. Beta is the next one out, so I got beta here, and this is beta. This beta has no hydrogens on it, so I'm just going to erase that off. That doesn't have a hydrogen on it, so that can't use that one, got to use one of these. So that base is going to come and grab a beta hydrogen from here. Electrons kick in to form a double bond and kick the halogen off. So that gets me one of my double bonds. That second equivalent will do the same thing with the other halogen, and we make the other double bond. So we're doing a double E2. This is just an E2 reaction. You're doing it twice. So right there's how we make it. First step, we're going to add in bromine to add across the double bond to give us the dihalide. Then we use 2 equivalents of a strong base to give me the diene. And then third step, I'm going to react with this dienophile, and that will give me the product. So for that one, I think that one was easier to work that one kind of, I went a little bit backwards to start with. I did a retro Diels-Alder, and then I tried to see how to get to one of those then. I think it was easier to see that way. So there's different approaches to looking at these. Questions on that one? this one here, I think, not an easy way to see this one. This one might just be kind of trial and error. First thing I would notice is I would count carbons and notice I haven't added any carbons. I notice that I've got the same number of carbons here as I do over here. So that's going to rule out a Grignard reaction or the organolithiums, because with those we were adding some carbons. So you think about the reactions that we've talked about reductions, oxidations, and then we did those organometallic compounds. So we've ruled out the organometallics because it's got the same number of carbons in the starting material and the product. We didn't add any carbons. So this has got to be some kind of reduction or oxidation. We've not covered any other reactions. Well, we did I guess we did too. We did the 1,2 addition and 1,4 addition, didn't we? But those were on dienes, and I don't have a diene, so that one's out. So it's got to be a reduction or an oxidation here, or maybe both. Let's see what we can do here. Well, here I have an ester. An ester, I cannot oxidize an ester any further. You think back what we did. You can't oxidize an ester any further. Oxidation, we were oxidizing like alcohols, or we could oxidize an aldehyde. So it can't be oxidation because it was alcohols or an aldehyde was the only oxidations that we did. Reduction, we did reduce esters, if you think back. So that's what it's got to be. That's the only possibility. That's the only thing that I got that can react. We have the ester that we can reduce. We have an ether. We haven't done anything with ethers in this chapter, in either of these chapters. So it had to be a reduction of that ester. Now, how did you reduce an ester? Our reduction of an ester, the only way they can reduce it, we had 2 reducing reagents. We had sodium borohydride and lithium aluminum hydride. Well, I guess we had 3. We also had hydrogenation. We could do hydrogen gas with platinum, palladium, or nickel. But the only one out of all of those that could do an ester was the lithium aluminum hydride. So it had to be lithium aluminum hydride that we're reacting with here, because that's the only thing that we've done on an ester. So let's see what happens. You can kind of work through that. So let's transfer a hydride in and see what we get. We kick the electrons up. Now, anytime we kick electrons up onto the oxygen, we always need to look and see, can they kick back in and reform the carbonyl if you have a leaving group. Here we have carbon-carbon bond, not going to break it. Here's carbon-hydrogen, not going to break it. But carbon-oxygen, we said, got a big difference in electronegativity. You will break that, so that kicks off. So we temporarily got an aldehyde. Kicked off the oxygen. It's still attached back here on the other side, but it's got a negative charge now. But we've made an aldehyde. Lithium aluminum hydride will also reduce that. So let's go again. You remember, lithium aluminum hydride can transfer all 4 hydrides. You can transfer up to 4. So this is going to go again. Now let's acidify it, neutralize it. We add in some acid, or just water is good enough. That's acidic enough. We'll just put in some water or any acid, and that will protonate these to alcohol groups. Okay, now we're making some progress. Now let's take a look. Is that getting close? And we're getting kind of close here. Now we've got some alcohols, and we need to get those to carbonyls. I have a primary alcohol, and we have a secondary alcohol. Look at the primary. The primary one went to an aldehyde. The secondary one went to a ketone. if you look. So what can take secondary, any of them worked on the secondary, any oxidant that we talked about will work on the secondary. But with the primary, we had a difference on primary. If you want to take a primary to an aldehyde, we use PCC or Swern. If you use any of the others, it went to a carboxylic acid. If you used chromic acid or potassium permanganate or any of those, it went to a carboxylic acid. But to stop at the aldehyde, this had to be PCC or the Swern. And you're welcome to just write PCC or Swern. You don't have to draw out the structures for that. Okay, so there we're finished. So we need first step, you're just adding in lithium aluminum hydride to reduce that. Second step, we'll acidify with some water or any other acid. You can do any acid there. And third step, we will oxidize it with PCC or Swern. And so that's what I was looking for. So that wasn't too bad. If you just think about, what was the only thing we've done with an ester? The only thing we've done on ester was a reduction. Or we did react with Grignards and things, but that was adding carbons. We didn't add a carbon. So it had to be a reduction adding a hydride. Now if there had been extra carbons over here, if there had been some extra carbons, been more carbons on this side than there was this side, then I'm going to start thinking Grignard or organolithium compounds as a nucleophile instead of a hydride as my nucleophile. There you're adding carbons. Okay, questions? Now you know I don't ever put the same thing on your test, so if I did a reduction there in the first step, then pretty good chance maybe you might have one of those with the organolithium or magnesium in the first step or something like that. So, if I could give the same thing, but more than likely I probably wouldn't. Okay, question 5. We are looking at a molecular orbital energy diagram. Let's first examine our compound here, see what we've got. Of course, the double bonds have got p orbitals, and that anion sits in a p orbital. So we've got 5 p orbitals, which would be 5 atomic orbitals. 5 atomic orbitals means we've got 5 molecular orbitals to draw. 5 MOs. Now let's look at how many pi electrons I have. I have 2 pi in this double bond, 2 pi in this double bond, and the anion, there would be a lone pair there that would give it the negative charge, so I got 2 more pi. I've got 6 pi electrons to account for. Now I've drawn part of the diagram already for you. I drew the hard ones, and you just have to finish it out, and I left you the easier ones to draw. The first one, the lowest energy one, should be easy. Our first pi molecular orbital. We're always in phase. Remember, we got 5 p orbitals to put on. 5 p orbitals. And we're in phase all the way across. So that's an easy one. 0 nodes. In phase all the way across. Now as you go up in energy, you increase 1 node each time you go up in energy. So we had 0 nodes here. The next one will have 1 node. Now you always try to draw your nodes as symmetrical as possible. So it's going to have to go right through the middle. There's no other option for it. It's got to go right through the middle, and it would cancel that p orbital out. The node would have to go right down the center, since I only have the 1 node. Now, color our phases in. I'm I'm going to start on top. When I cross my node, then we switch to the bottom. Okay, there's our second molecular orbital. I already had the others drawn in here, the other two, the next two, I mean. Let's just look at them real quick. So this one would have two nodes. So we had zero nodes, one node. This would have two nodes. Try to get it as symmetrical as possible. And you try to avoid going through the orbitals if at all possible. So I'm going to stretch them out here. And then that makes it pretty symmetrical. And so this is that one colored in. I already had it on there for you. So that one's a little bit difficult to see. And then our fourth one. So this one would have three nodes. So one of those is going to have to go down the center. And that would be our three nodes. And then finally the last one, that one you have to draw in. And I left that one on there blank. So the last one should be easy. We said the last one just alternates. You don't even have to think about it. It's just going to alternate all the way down. Top, bottom, top, bottom, top. It just alternates. Now that one would have four nodes if you wanted to show them. You don't have to. But it would have four nodes, and you can see where they would be at. Now let's put our electrons in. We had 6 pi electrons to put in. So you can't put more than 2 in an orbital. We'll put 2 in the lowest energy, then put another 2 in the next lowest, and finally 2 more here. And that's all you have to draw. That's the full energy diagram. Now we can put more information on there, but I just asked for the energy diagram. If you wanted more information, these bottom two happen to be bonding MOs. And the top two are anti-bonding. And the one here in the middle is a non-bonding. You only have non-bonding when you have an odd number of molecular orbitals, and we do have an odd number here. We also talked about HOMO-LUMO. HOMO is the highest occupied, highest that has any electrons in it, so this one would have to be the HOMO, and this one would have to be the LUMO. If you wanted to write that. But I didn't ask for that. I just asked for the energy diagram. So all that you had to show was what I had there. There in black. That's all I asked for. Was to finish out drawing the orbitals, the molecular orbitals, and put the electrons in. Questions? Of course, I could ask you to identify the bonding and non-bonding. I might give you the full diagram and say, just identify HOMO and LUMO. I could do that. Or say, identify HOMO, LUMO, and identify the bonding and anti-bonding, non-bonding. I can do that. So there's some different ways I could ask that. Okay, we got some more. Next one here, we're looking at some retrosynthesis. So I'm giving you only the product, and you have to give me the starting materials. Any questions on the molecular orbital diagram? You're all quiet. You're supposed to ask questions. If you're not going to ask questions, I could have just, you didn't even have to be here. I could have just recorded it.
I have a question.
Yes.
Would the last two always be the HOMO and LUMO, like the last two up here?
No. It would on this one, but, you know, it depends on the molecule itself. Mm-hmm. You know, if I had, so we did this anion. If I had done the cation, then the cation only has 4 pi electrons instead of 6.
Right.
So the orbitals would be the same, but you've only got 4 pi electrons instead of the 6, because that one's empty. So now for this one is the HOMO, and this one is the LUMO. So they can change. It's just HOMO is the highest one that you have that's got any electrons in it.
Okay.
LUMO is the lowest one that's empty.
Okay.
Other questions? Finally got a question out of you. Out of somebody.
Does the HOMO have to have 2 electrons or just 1?
HOMO is just the highest occupied, so it can be 1 or 2. Highest one that has any electrons. That's a good question. LUMO is just the lowest one that's completely empty. Nowhere did it say how many you got to have. It's just highest occupied, lowest unoccupied. So it doesn't talk about how many electrons you have. That's also a good question. See, y'all come up with some good ones if you'll just ask them. Okay. Question 6 here says we're going to do a retrosynthesis, and it gave you a little hint. It said to use the appropriate organometallic reagents. That it can be either Grignard or the organolithium. You can use either one. So it told you what type of reaction we're going to be doing. Now, if you recall, for the Grignard's reactions or the organolithium, I told you to find the OH, find the carbon that it's attached to, and then break it apart right past that. Now we have to figure out where to break. We don't want to break rings, because then you're going to have to try to get to close up and make a ring. Then you got all kinds of problems. I want to break off that methyl. I just need to be able to, I just need to break past the red carbon there. So technically I could break on any side there, but it's going to be a lot easier if I just take off the methyl, break down there, make that my Grignard or organolithium. Or you can have that as methyl lithium. Either way is perfectly fine. And then the rest of this will be, so there's where we cleave, the rest of this will be the carbonyl. So I'm going to make this a carbonyl bond right here. Take the hydrogen off, make that a carbonyl. You can leave the rest of that just like it is. Added an extra carbon, didn't I? So right there, I'm going to make that my carbonyl. Make this bond here the carbonyl. I cleaved off the methyl, made that the carbonyl. So methyl magnesium bromide plus that ketone, or the methyl lithium plus that ketone, will give that product. Questions?
Will we ever have a problem where we have to break a ring for the retrosynthesis on the exam?
It's a possibility, but it would be extremely rare. I was trying to think if I've ever done that on a test. I probably have. That's pretty hard. I'm not mad at you all right now, so I was probably mad at them that semester. They did something that made me mad. You ask anybody in the spring, last spring semester, boy, I got really mad last spring, and I gave some nasty tests to finish the semester out. Because that's, we shut down last March, and we had to go all online, so I had my test online and they were all cheating. And boy, I got nasty then. So I was like, if they're going to work together and cheat, I'm going to make certain that nobody passes it. I didn't get that bad, but it was pretty bad. Oh, I had a lot of cheating going on. I took care of it. The ones that I could definitely see that had cheated, they all got zeros on the test. I gave a lot of zeros. That last test, test 4, I think I had probably close to half the class got a 0 on that test. Okay, continuing along. So don't cheat on me. I have no problem giving a 0. I don't want you to cheat your way through and you get to med school and go become a doctor one day, and I'm in a car wreck, and I wake up and there you are standing over top of me and getting ready to operate, and I'm like, oh man, that's the one of the students that cheated their way through. They don't know what they're doing. Plus, it's not fair to the ones that are working right. I don't want somebody to take a spot out of med school, cheat your way in, and take up a spot with somebody that really deserved it. Okay, let's take a look at this one. So this one said to do this one by Diels Alder. It gave you a hint, told you that this was Diels Alder. Make this product doing a Diels Alder. Now we happen to have a bicyclic here. That makes it a little tougher. But as we talked about this morning, go find the double bond that's in a 6-membered ring. Extend out 1 carbon on each side and then cleave. Okay, I've got 2 double bonds. Let's see what happens here. Find one of them. It doesn't matter which one you use. The molecule is symmetrical, so it didn't matter which one I used. So let's use this one. I'm going to highlight those. There's my double bond that's in a 6-membered ring. Extend out 1 carbon on each side. And then cleave that off. I'm going to show it both ways here just to show you. Now, potentially I could cleave to the top or I could cleave to the bottom here, and it is going to make a difference. And I'll show you both ways, and I think you'll see quickly once I do it why one way will not work. Let's do this one first. So I could cleave this direction. So find the double bond, extend out 1 carbon on each side, and then cleave. So the 4 green ones there are going to be my diene. Pull this out, and that's going to be the diene. We'll make that the diene. And that still has these 2 carbons up here at the top, in between. Right there, so I'll just put those. So there's our diene. The rest of this would be, what we cleaved off would be the dienophyte. Now you notice there's a double bond here. Normally there's a single bond out there because a Diels Alder reaction, normally it's a diene reacting with an alkene, and you move the electrons around and you make a ring with a new double bond, and then that double bond here became a single bond. But we're left with a double bond. So if you recall back what we did, we said alkynes also work, and if you do an alkyne, then you're left with a double bond. So this had to be an alkyne. This was an alkyne. So this alkyne and that diene will react and give that product. Now, as I mentioned, we could possibly, it is a possibility, that I could have cleaved into the other ring. So found the double bond, extend out 1 carbon on each side. What if I had cleaved here and here? I'll put that one in red. If we had cleaved there and there, let's see what happens. Well, the top part here has to be the dienophile. So let's make this my double bond, these 2 carbons. There's my dienophile, nothing wrong with that. And then the rest of this at the bottom has to be the diene, and so we're going to make these green carbons here. We got to make those a diene. But it's still got the rest of this hanging on. Do you see the problem now?
Trying a really stable benzene.
It's a benzene ring. Benzenes don't react. That's aromatic. We learned last semester those don't react. We will do some reactions on benzenes coming up. We got a chapter where we get some reactions going, but this is not going to work. you cannot do a Diels-Alder on a benzene ring. So it's got to be the top one there. So it didn't matter which way you broke that. Questions?
Why did you choose the double bond on the right and not the one on the left?
It didn't matter. It was symmetrical. It would give you the exact same thing either way. Because there's symmetry in that. It would not have mattered one bit. You'd have the exact same thing. So if I had, if I chose this one and extended out one carbon on each side and then cleaved, then that would have still gave that diene, and this would have still become that alkyne and been the same thing. So it didn't matter. So you could have went that way. Same thing. Other questions? Okay, let's look at some reactions. Our first reaction, so with the reactions, you just have to give me the major product. Should have stated that. Usually I do. I didn't say that. I said give the organic product or products for the following reaction. All I care about is the major. I'll make certain on your test it says give me the major organic product. Now that's all you have to do is give me the major product. But just like last semester, some of you didn't have me last semester, so you took organic one elsewhere. So I just want to mention, all I'm looking for on my reactions is the major product. But the more information you can give me, gives me a chance to give you some partial credit. I am really good at partial credit. So, I would kind of work through it. Show me a little bit of mechanism or something, and then even if you got the wrong product, I can give you some partial credit. If you got started correctly, but then messed up along the way, I can give some partial credit. Oh, I forgot. We were not going to do 8A because I said that was a section I skipped this morning. Yep, let's forget about 8A because I skipped that section this morning. It's got something in it that we didn't talk about this morning. I skipped that section. So let's go on down to B here. Okay. Now, one thing that stands out to me here, notice that over here on our first step, we're adding ethyl magnesium bromide, and it says excess. That means you have all that you need to do anything. So they're not just one equivalent. There's an excess, so there's like 10 equivalents in there. So there's plenty of ethyl magnesium bromide to do whatever you need to. That would take care of any acidic hydrogens. If you happen to have acidic hydrogen and you destroyed one, there's an excess. That means you got a lot more than what you need. So even if there's acidic hydrogen, some got destroyed, you still got plenty left. Or maybe you're adding more than one to something. So there's plenty of it in there, excess. Okay, so let's see what we've got. Got a carbonyl, partial positive charge on the carbonyl, partial negative on the oxygen. With the green yard, partial negative on the metal on the carbon attached to the metal, partial positive on the metal. So it's that ethyl group. That ethyl is attracted, with the partial negative, is attracted to the carbonyl carbon because of the partial positive, and we kick the electrons up onto the oxygen. Stuck an ethyl group on there. Now, anytime we kick electrons up onto the oxygen, we should always look and see, can those kick back in, reform the carbonyl if you have a leaving group. Here to the bottom is a carbon-carbon bond that we just formed. We're not going to break it. Carbon-carbon bonds you're not going to break. But here to the left or to the right, we have carbon-oxygen bond. You're going to break one of those. no matter which one you do, I'm going to take off the one here on the left. We're going to break that bond. We kick that off and we reform the carbonyl. Okay, so I made the carbonyl back. Now remember, we had an excess of the Grignard. And I have a carbonyl again. So just like we did here to start with, we're going to do the exact same thing down here. I will take more of the Grignard. There is excess. And it's going to do the exact same thing again. It's going to attack the carbonyl carbon and we're going to kick the electrons up onto the oxygen. Put negative charge onto that oxygen. Now, anytime, just like we did over here, anytime we kick the electrons on the oxygen, we need to look and see, just in case, can they kick back in and reform the carbonyl if you have a leaving group? Here to the left, carbon-carbon bond, not going to break it. Here to the bottom, carbon-carbon, not going to break it. But to the right, there's a carbon-oxygen bond. We are going to break that. So I have another leaving group. And we get a carbonyl back. I've got a ketone now. Now remember, there was an excess of the ethyl magnesium bromide, so there's plenty around. And I have another carbonyl again. So this is going to go again. Ethyl group. Attacks the carbonyl carbon, kicks the electrons up onto the oxygen. Now, anytime you kick electrons on the oxygen again, check and see if they kick back in, can they reform the carbonyl? If they kick back in, is there something we can kick off? No, it's carbon-carbon, carbon-carbon, carbon-carbon. It's finally done. Finally finished. Stop. Now, last step, we're adding in acid. And so that will protonate your oxygen. We'll do an acid-base reaction. There's your final product. Finally, I'm finished. So that one had a lot of leaving groups on there. We could just keep reacting and keep reacting. Wound up putting 3 alpha groups on. Questions?
Would you incorporate the leaving curve into the final product? Like this?
I'm not worried about it, but if you wanted to show it, I mean, this is what we're aiming for. But the group that we kicked off, this is what we kicked off. And so it would also get protonated. So yes, there would be some phenol in there as well. Now the only time you need to show the I consider that a byproduct. This is what we were, the original carbonyl that we were trying to react. The only time you need to be worried about the byproducts is if I had started like with a cyclic ester and the leaving group is still attached back on the back side, then you have to show that. But this is just considered a byproduct and it got, we can wash that away. Boil it, probably do a distillation and boil it away. Because those would have different boiling points and so we can do a fractional distillation. Yes?
It's been an hour. Do you need to change your battery?
I've got another 5 minutes according to my watch. I think it's still going there.
It is.
Okay, I've got another 5 minutes. I'm trying to record as much as possible and then I'll switch out and I'll give you all a break too. It's been a while. If you need to go to the restroom, take a little break. Okay. Next one here, we have a two-step reaction. Don't freak out, just take them one step at a time. First step, I have chromic acid in there. This is chromic acid. It's got acetone as well. Acetone, you know, we've dealt with acetone in the lab. We use it to wash with, but it's also a good solvent. That's why we wash with it all the time. Clean our glassware, it's a good solvent. This is going to be the solvent. So chromic acid is a good oxidizer. Very strong oxidizer, so let's see what we can oxidize. We have a secondary alcohol here, and I have another secondary alcohol. So we're going to oxidize those alcohols. Those alcohols get oxidized. The secondary gets oxidized to a ketone. That's the only thing they can go to is a ketone. So there's our product after the first step. Second step, I'm reacting with a diene. Now, my diene, if you look at it, it is right now, it is currently in the S-trans conformation. We're going to do, you know, with a diene, anytime you see a diene, you just instantly think, hey, Diels-Alder. You're going to think Diels-Alder reaction anytime you have a diene, but with Diels-Alder they need to be in the S-cis conformation. So let's rotate around this bond to get it in the correct conformation, and then we'll react it with the molecule that we made up here. So we're going to do a rotation around that single bond and get it into a diene. Now we need to make certain those methyls point the right way. And if you look, this alkene right here, this has got a methyl and this group here coming off the same side, so that's a cis alkene. This one's got a methyl coming down and this group coming down as well. These are on the same side, that's also a cis alkene. So they need to be cis after the rotation as well. We're not changing the red part, we're only changing that green part right there from S-cis to S, from S-trans to S-cis. These cis stay the same. So we know that these methyls had to be pointing inward. And then that is still a cis double bond, and this is a cis double bond. And our molecule is in the S-cis conformation. So the single bond is also cis. Now we're in the right conformation. So I'm going to bring this molecule down here before we can see it react. So I'm going to take our product here from the first step and react with the diene here in the second step. And so we know the mechanism for a Diels-Alder. So we form a 6-membered ring with a new double bond. And I just need to put the junk on. Now this one does say show stereochemistry, so that you know you only have to show stereochemistry where I specify. You don't have to show stereochemistry anywhere else, only where I say show stereochemistry. Wherever I put that, you better show me stereochemistry. I'm going to count off. Now, these 4 carbons that I've got in green, that's these 4 here. And the 2 in blue, that's these 2 here. Notice our methyls were pointing inward. So we talked about this morning. If these groups are